All right, so our group decided to go with the Twitch dataset that was recommended by the professor, where we are trying to predict what streamers' users, which are given by an anonymized user ID, will watch based on their watch history of various streamers and the time that they spent watching. To evaluate this model, or some baselines that we wanted to use for this model that stood out, were the rep baseline, where we basically just look at every user's history and just recommend whoever they've watched the most, as well as the pop baseline, which will basically just recommend the most popular streamers to every single user. These were the baselines to beat, and as you will learn, they were quite tricky. So this is the Jupyter notebook that we put all of our work into. The data, we loaded it in. We went with a smaller data file because the full 4 million users that were available were too much for us to really handle in the time that we had. So we went with a smaller 100,000 user data set. We pretty much simply just loaded it in and processed it into a pandas data frame and assigned indexes for each unique user and streamer. We then processed the data into a training and test split that we split temporally. So we basically just took the bottom or the oldest 90% of the entries and considered those our training data and reserved the last 10% of stream interactions representing the most recent occurrences as our test set. So you can kind of consider our model existing in a single point in time. So we also calculated what we called a user concentration score. It essentially is a number from 0 to 1 that represents sort of, you can think of the loyalty of this user or how widely dispersed their viewing minutes are over the different streamers that they watch. And this became useful in one of our evaluation metrics and in one of the models that we decided to use later. Here is the histogram of the distribution of these concentration scores. This is a bit massaged. We wanted a good even spread because it helped the model that we were training later. Okay. For our exploratory analysis, we started with some intuition building on the data set of 100,000 users. We wanted to know who the most popular streamers were. At the time, it was Ninja, by far. We also wanted to know how often it was that people would view new streams. Baselines like rep are really good at recommending streams that the user already likes. So we wanted to know how important it was or how common it was for users to actually watch new streams. And by our analysis, we found that it was about 49% of the viewing instances in the data set were brand new. That streamer user pair had never appeared before. We'll then move on to our evaluation engine, which we used. Our main metric, the metrics that we were looking at were the hit at 1 and hit at 10 metrics. Basically, if the recommender could recommend something that the user would watch in the test set, in the first 10 recommendations, that would be a hit at 10. If it got the first one correctly, that would be a hit at 1. We also wanted to keep track of the new recommendations that we would make. Baselines like rep can perform really well, but they perform really poorly at recommending new streamers to users. So we wanted to have a metric that measured that as well. This is some visualizations that you'll see in just a moment. So here are our baseline models, the simplest ones. The rep model, the way we implemented it actually will do rep for as long as it can and then default to pop. it basically will just give you the most watched users in a user's history, or most watched streamers in user history. And as you can see in evaluations, it performs very strongly on general items. It's a pretty dumb but pretty effective baseline. But when it comes to new items, it barely can recommend anything. It by default can't. This small figure here is basically running out of recommendations and falling back to pop. The popularity model, on the other hand, is actually pretty poor, but it will perform better at recommending other newer items in RepWell, at least. These are our visualizations that we use to kind of analyze the effectiveness of every model that we tested, and model and baseline. We have its performance at various values of K, so various hit at metrics. We can see how it biases streamer popularity. Here you can see the popularity for pop is, in hit at 1 is just a single bar. It only gives you the most popular streamer, Ninja. And after that, it doesn't matter. It's always going to give you the top 10 streamers. This chart over here is pretty interesting. It shows that concentration score that we came up with, how it affects performances. So it's a scatter plot of whether this benchmark was hitting or missing. Rep, as you can see, pretty solid across the board for its hits, although it does start to, you see it will miss less for the users that are very loyal. So that means if users are watching the same streamer a lot, they'll have a high concentration score, and generally rep will not perform poorly for those users over on this end. And you can see that a little bit in the scatter plot. On the other hand, pop just performs poorly everywhere. But it does seem to do a little bit better, or it does seem to do even worse with the users with that high concentration score. You can see there's almost no hits over here. The users that really like one streamer in particular aren't really interested in the most popular streamers. First actual machine learning model is alternating least squares. We essentially just used the model from the implicit library. These factors were kind of chosen at random. They seem to work well enough. We didn't mess around with it too much. This was more of a baseline that we wanted to find. One interesting tweak that we did make is a ALS discovery mode, where essentially we just filter out any items that the user has already liked or has already seen being streamers. So we anticipated it to be a very high baseline for discovery, because it just won't recommend anything that the user has already seen. But it will compare users that are similar to the user that's getting a recommendation, and basically recommend streamers that those other similar users are into. With ALS, we wanted this as a benchmark for what we thought would be a hard benchmark to beat for discovery. These graphs might be a little bit distracting. The really important number that we want to look at here is our hit rate for new streamers. 2% for hit at 1 is not great, not terrible. For hit at 10 though, 23% on new streamers was actually a pretty strong figure. And when we implemented this discovery mode, where we basically only looked at streamers that the user hadn't seen before, the numbers got pretty good for this novel hit rate. Especially when you gave it enough time to kind of find something. You can see the climb for the discovery mode is steady, but it winds up usually recommending, I shouldn't say usually, it it winds up performing well at recommending new streamers to users. To introduce our first more powerful model, I will turn it over to our group mate, Alex Cojocaru.
Hi everyone, I'm going to be going over matrix factorization using the Bayesian personalized ranking. And this also includes uniform negative sampling, which was a preliminary model in the research paper where the data came from. So in order to train this model, we needed to get interactions of user indices and item indices, which is what this line does here. And then for each user, the streamers they consumed, which are the item, which is user consumed items here. And then the important part is the sample negative batch, which for a p-repeat chance, so for a 50% chance, which is what the research paper authors found as the best chance, we will either sample negative items from the streams that the user or the streamers that the user has consumed before, or if not, then we will just stream or we will sample negative items or negative streamers from the total set. So that's what this sample negative batch does. And this is just a wrapper function to make it efficient for TensorFlow so that it can do it in batches and vectorize it so it's faster. And then the MF model class is using TensorFlow, and we have three main variables, beta I, gamma U, gamma I, which is typical in matrix factorization. And then these are the usual functions that are included, the regularization, the score, and then the call. So all of this stuff is just the matrix factorization model in TensorFlow. And here at each training step, what we do is we apply the gradients, and yeah, we get the UIJ, user item, and then the negative item, and we apply the gradients. So in order to do that, we create a data set with TensorFlow, and then we use the negative sampling to get the negative items. And then here we have the variables or the hyperparameters we used, and some of these came from the paper. Create the model, compile it, and then fit it. So this was training the model. And then here, this just evaluates the model using the hit at 10 and hit at 1. So for all this work, there was not much accuracy. It was very, very low. This could be due to a variety of factors. Perhaps the hyperparameters were bad, or the model itself may not be good. But as we'll learn later, a simpler approach was actually way more effective. The hit at new was only like right here, 0.1% and 0.45 for all items. And at 10, the hit at 10 was doing a little bit better, but still not that good. Only 14% and about 5.3% for new items. And here are some graphs for reference to compare to other models. That's it from me. Thank you.
So after all that work without much payoff, we tried to do something a little bit different. We essentially just flipped a coin. So we had two baseline models that performed really well at either recommending something new or recommending something that the user has already shown to be interested in, rep and ALS random. And so our next strategy was just stochastically choose one of them and give them to the user as a recommendation. We just generate a random number and use that in deciding whether we're going to use rep for next recommendation or use ALS with the discovery option for ALS. And this performed really surprisingly well. hit rate at all items wasn't nearly as strong as rep, but it performed decently well at recommending new items. And when you expand it to higher, a higher range of hit rates, the randomness kind of had a chance to give you the best of both worlds. So we saw overall hit rates of 77% within the top 10 recommendations and 21% for new recommendations. It's simple, but it works. We added a little bit more complexity with that concentration score that we mentioned earlier. Essentially, we would call that concentration score with the training matrix, which is basically the matrix of all kind of minutes spent watching a certain streamer that is given for each user as a row. And we would use that concentration score to essentially set the benchmark for the coin flip. Oh, wait, not there. We can use that concentration score, or aka the diversity score, as the benchmark for the coin flip. This wound up performing fairly well. We got a much better hit rate, new only, for our hit at one metric. The performance of overall hit rates did suffer a bit more. This is now sitting about half the effectiveness of just rep alone, which is to be expected, but we found that this was a pretty nice sweet spot for giving something usually that the user might want to see, and having a good chance of giving them something new, especially when you gave it more time to get something that might work. And one big benefit of this is this was fast. This took almost no time to train. It by far outperformed the more advanced machine learning model in pretty much all metrics. So sometimes less is more.
The dataset we use for our recommendation system originates from the prior study on live stream recommendations by Rapaz, Macaulay, and Eber. In their work, they created the dataset by collecting over 400 million user-streamer interactions on Twitch across a 43-day time period. In the study, the authors initially used the data to analyze user behaviors, including daily, weekly, repeat watching patterns. The prior work has used very similar approaches to ours. Earlier studies on live streaming recommendations also relied on simple baselines such as pop, popularity, and repeat consumptions. These baselines are commonly used because pop measures how well a model does by recommending the most popular items overall, while rep captures the fact that users often return to the same creators, which is especially true on Twitch. The original paper also used the same ranking metrics to evaluate progress through hit at 10, or hit at 1, hit at 10, and NDCG, normalized discounted cumulative gain. Because these baselines and metrics are standard in prior research, the earlier study used them to evaluate their models. We also follow the same approach to maintain consistency and comparability. Our results match their rep and pop model, but our more advanced models tend to differ quite a bit to their more advanced models from the reported related work, as we can see here. Their optimized live rec plus rep and AV completely blew ours out of the water, but it was mainly due to the time to tune, the amount of training data that we used. They used the whole training data of 400 million interactions by users, while we only limited ours to about 4 million user interactions. And yeah.
All right, that's all we have for you. Thank you for joining us through this exploration of building a recommender system based on Twitch.tv data. We found it interesting. I hope you found it informative, and I hope you have a wonderful winter break. Cheers.